Let me record. Okay. So I have a brief PowerPoint presentation on the lock-in amplifier that we touched on at the end of last lecture. So the lock-in amplifier is going to be what you guys are working on for all of Lab 5. If you guys noticed, I uploaded that. It's going to be in 2 different sections. The first section being working in MATLAB, going over what you would have done in lab roughly, and watching a YouTube video of someone actually working with the instrumentation you would have worked in lab, and answering some questions about some demo experiments they did. So trying to have some lab aspects even though we're not in lab. And then next week there will be a simulation that was developed at the University of Pittsburgh. That's a little more hands-on. It would be similar to some of the settings you would be changing on the lock-in in the lab to give you an idea of what some of the output would look like. But in this lecture, we're going to be going over more of the background or the theory behind it, some of the math behind the lock-in. We're first going to go over what are the different ways that lock-ins can be used. There's different methods you may apply them to. It's important to know what are the key electrical components that go into a lock-in amplifier and what mathematical functions they perform. We're going to go over the mathematical principles of how the lock-in works in detecting both the frequency of a signal and also the phase. And then finally going over quantifying the quality factor or the frequency response of the lock-in, and a little bit of what the functions or what the buttons or what the different components are of the lock-in that you guys would have used. This is highlighted in lab tomorrow as well. A lock-in amplifier is a very sensitive instrument that you can use to detect very low signal to noise ratio signal. So we talked about that last week when we were going over all the sources of noise. And it's done by comparing an input AC signal to a reference. But some of the applications it's used for is very sensitive AC voltmeter, where it can range all the way down to nanovolts. You can also detect the phase of your signal compared to this reference signal very precisely. You can record the frequency response of your signal or a sample. And I highlighted yesterday, and we'll go over later, it's a very high quality bandpass filter. So way better than you can perform with the bandpass filters you guys constructed in lab previously. And then, so to illustrate this is a noise spectrum that we sketched out last week. So as a reminder, I'll ask you guys, this portion here, less than 100 Hertz, what type of noise is abundant there?
Pink noise.
1 over F.
Yeah, 1 over F noise. So the flicker noise is there. This offset here in the noise spectrum, greater than 100 Hertz, what's the contribution of this constant offset here?
Thermal.
Thermal noise.
Yeah, so there's thermal noise, and what other white noise source was there?
Shot.
Yeah.
Shot noise.
So that's thermal and shot noise. And then these little peaks, what are those, what source of noise is that?
Environmental noise.
Yeah, so that'd be environmental noise. So there's a 60 Hertz signal from our electrical wires, and then radio signals over here for environmental noise. So with a lock-in, you're able to have a very high Q bandpass filter. So you can really select out a very narrow band of frequencies if you know exactly where it lies, and ignore all the other noise. So we'll be going over quantifying that based on the bandwidth and the center frequency there. So it's also useful for noise measurements. So the lock-in amplifier you guys would have been using is a Stanford Research Systems SR510. This is the front panel of it, and you guys will be going over this in more detail in lab tomorrow. But I just wanted to point out with some of these uses here and some of the ranges that I mentioned, the sensitivity you can notice the sensitivity here on this panel where it goes down to, it goes 1 to 500 here. So you hit these black buttons over here, and then the range here goes millivolts, microvolts to nanovolts. So it's very important when you're using these not to overload the sensitivity here. You have to have the right range selected, and also this is a dynamic reserve or the dynamic range that we discussed in the last lecture as well, that you can easily overload this. And then with the phase sensitive measurements here, this is where you would provide your reference signal and you can tune the phase of your signal. So this is a 90-degree step, and if you want more precise changes in the degrees here, you would hit these buttons. So this is how you would use it as a phase meter, of shifting the phase of your signal. But the principle of this lock-in that I mentioned, you're always comparing an input signal that you're interested in to a reference signal. And it's important that your input signal is an AC signal. So if you are interested in a DC signal, you have to convert that to an AC signal. So if you were doing this with an electrical signal, you might have to use a summing circuit. If you were using an optical measurement, you might have to use a chapter. You'll see this in the video tomorrow, to create your signal so that it's AC. And the important thing of the reason you want an AC signal is looking at differences is much easier than looking at a constant value. And if you have a DC signal, the background, the noise, it can drift over time. So it'd be difficult to understand that signal if it's drifting around. So the AC signal ignores that drift. So you need an AC signal for your input there. So that's one key thing that you need for a lock-in amplifier is an input AC signal, and I'm going to represent that by a sinusoidal function here with an amplitude, a frequency, and a phase. You're then comparing that to another input that's going to be your reference AC signal, and this is, it can be a sine wave, but it can also be a square wave as well, and we're going to say it's going to be at a frequency of omega-2 here, and it doesn't have a phase. So we're only going to be changing the phase of our input signal. So you have to have these two input AC signals. The other key component is going to be a multiplier. You want to multiply these signals together. So we discussed this last week, that the first one thing that you need, a mathematical function that you need for a lock-in, is to multiply these signals together. If you were doing this in the lab, you guys would have done a home-built circuit with an op-amp. So this would be the 8633. So tomorrow you'll take a look at the user manual for that and see what pins, what output you would be looking at with that multiplier. So if we take this multiplier, we would take this A sine omega 1 t plus phi. That's going to be our input AC signal multiplied times that reference signal. So the mathematical function you first do is multiply the signals together. The next thing you do is you integrate those signals with a low pass filter. So this is our frequency response function for a low pass filter. This should look familiar. And what you're doing is, after you multiply these signals together, if you integrate them, well, I guess first thing is we can take these multiplied signals together, and we can use this trig identity here to write this expression in terms of two cosines. So if we apply that to our multiplied signals, we then get this expression here. So this left-hand portion here, you can see that the two frequencies are subtracted from one another. So this would be a very low frequency, while these would be added together, this would be a higher frequency. So when you take your low pass filter and you integrate this together, you want to select a condition where the cutoff frequency would keep this low frequency component, or if you are at close to the same frequency between your input and your reference, this would be close to DC. And this would then result in A over 2 times cosine of the phase if you had these frequencies approximately the same. And then also with the cutoff frequency of your low pass filter, you want to remove this second higher frequency component up here with the sum. So when you integrate, if we plot these two components here on our frequency response function, this is what it would look like. It would cut off the higher frequency component. It would keep this lower frequency component. So if all these conditions are met with, if you select your integrator appropriately, you'll then be left with a DC component. And then in many lock-in amplifiers, the commercial one that you guys would have been using, there would be a DC amplifier as well. And then you would get a DC output for the signal. And you only get a DC output when you select your integrator appropriately and when these signals are locked in together. So their frequencies are matching, their phases are matching, you get a DC output. So that's where the terminology of locked or lock-in comes from. So any questions here of the different components that are in the lock-in? Okay. And then this math down here is the important aspect of the frequency dependence or the frequency selection of the lock-in amplifier. But we can also apply this to phase sensitivity as well. So we have the same input signal and reference signal here that are multiplied together. This is just the same expression written again. And let's say that we have the same frequency for our input and our reference signal. We can then, this term here would then be equal to 0, and we can write this as a/2 times cosine of phi minus a/2 cosine 2 times the frequency times t plus the phase. So again, if we select our low pass frequency filter, our integrator to the appropriate settings, this would then be filtered out, this second term, and then we will be left with this a/2 cosine phi term. And if we think about the dependence of cosine based on the phase, we would have a maximum when these are at the exact same phase or 180 degrees. But if they're 90 degrees off of one another, if they're out of phase, we would have a 0 output here. So this is the mathematical principles behind the phase sensitivity of the lock-in amplifier. Okay. So to illustrate this, I have a couple of example plots of what a reference signal, an input signal, and then what the output would be for a lock-in amplifier. So if we have a reference signal here of a square wave, I mentioned it could be a square wave, it could be a sine wave, and we have input signal that is exactly the same frequency and exactly the same phase. First thing we're going to do is multiply these signals together. So we have a positive signal here times a positive signal, negative times a negative, positive times a positive. So we'll get an output that looks like this, of entirely positive signal. So this would be our multiplied signal. This is what the multiplier would be doing, or the multiplier is also called a mixer or demodulator. So the 8633 mixer would result in this. And then the important thing is when you're selecting the cutoff frequency of, or the time constant of your low pass filter, it's important to choose something that's averaging over many cycles of your signal. So to illustrate the integration, I have like this gray shaded box here, but it's going to average over many periods of the signal here. So what your output is going to then be the time average of your signal here. So there's a selection I'll show you on the front panel again that you can usually select this from 1 millisecond to 100 seconds, but it's very important to choose this relative to the frequencies of your signals. So this front panel here, you can see, again, pushing these black buttons, you can go down from 1 millisecond. I don't know why Stanford Research Systems, they use this capital S for seconds, but 1 millisecond up to 100 seconds here. And in this use, this is being used as an AC voltmeter. The output here is going to scale with the signal. So if you half your input signal, the area under this curve is going to be, once you multiply them and sum it all together, it's going to be half. If you double it, your output is going to double. It's so if we shift our signal 180 degrees here, so we have a negative times a positive or a positive times a negative, what would you guys expect for the multiplied signal here compared to the last
All
slide?
negative.
Yep. So it'll be all negative here, and our output would then be a negative DC signal. So when they're 100 degrees out of phase, just the output changes sign. And then how about if we shift these by 90 degrees? So here we have both positive and negative being multiplied by this positive. How would you expect the symmetry of that?
So you can just a sine wave then?
Sorry?
Will you get a different type of sine wave?
Yeah. Like it
So
won't, like it is.
Yeah, so it won't be exactly a sine, but it will be symmetric around y equals 0 here. So the important thing here is that then once we integrate all of this, sum it together, the output's going to be 0. So it's important to average over many periods. If you had a time constant where you would only be summing, let's say, half a period together, integrating over half a period, you would have something that would fluctuate and be an AC signal going from positive to negative, positive to negative. So here, this is when the lock-in is acting as a phase-sensitive detector. So your output voltage will tell you something about, is your input and your reference in phase or not. And then the last plot I want to show here is when you have different frequencies between your reference and your input. So you can see here that I've written the reference signal is 10 cycles while the input signal is 11 cycles. So they're slightly out of phase. So you could see where these dashed lines are being drawn, that it's not always lining up. So when we multiply these signals together, you get something really funky that it's shifting from being mostly positive to kind of symmetric around y equals 0 to mostly negative. And again, this is where it's very important to average and select your time constant appropriately. So if you average over enough cycles, you will get a 0, but if you don't choose that strategically, you'll get fluctuating signal. So the aspect of a lock-in working as a frequency detector is really tied to Fourier's trick that we went over when we were talking about the Fourier transform. That if you have an integral of the product of two cosines, if these integer values are different, it'll average over one period to 0. But if they're the same, you'll actually get a positive value. So again, this time constant, if the shaded box here, I'm showing that you need to average over at least 5 periods of the reference signal. You can see over here, it's mostly positive, then it's going to negative to get the 0 output. But if you only average, let's say, over 3 periods, you would get a positive value, then mostly negative. So you always want to err on the side of a longer time constant than a shorter time constant. So to illustrate this, quantify this, an example would be if you had a signal that was at 1000 hertz versus 1001 hertz. So the period for these is around 1 millisecond. So they would come in and out of phase every 1 hertz or every 1 second. So it's important, if you have these type of signals, to have your time constant much greater than 1 second. So using these lock-in amplifiers, sometimes you have to average over longer times and you have to wait for the output. So if you had these kilohertz signals, you'd have to be waiting every 1 second to collect a data point there to actually get the 0 output. If you didn't select your low-pass filter time constant correctly, what you would see, again, like I mentioned here, it would be your output, there's an analog output on these lock-in amplifiers. You'd actually see it oscillate back and forth from a positive to a negative value. So if you're getting an AC signal out from your lock-in amplifier instead of a DC signal, it's telling you that either your signals aren't locked, or it's also telling you that your time constant might not be correct. So that's an area to explore and adjust of getting your time constant correct to see if you get the DC output that you want. And then you can use the lock-in amplifier, like I mentioned, like a bandpass filter, where you're using that time constant. You can, we define this quality factor back with the bandpass filter of your bandwidth and your center frequencies. So again, if we think back to that 1000 Hertz signal and the time constant of 1 Hertz, we can quantify the Q value there. So this would be 1000 Hertz divided by 1 Hertz would be our Q value. So we get a very high Q value of 1000. So if you guys think back to lab 3 and when you guys were trying to get your quality factors, I remember lots of you guys were calculating it, measuring it on the LCZ, getting values all over the place, but I think the highest values you guys were getting were maybe around 10. But that was even a challenge. You guys were doing capacitors in parallel. There was a lot of trial and error of selecting your electronics. So I would say with the bandpass filters, 50 is what you could get at best, but that would be a challenge.
We accidentally got 83 on one of ours.
Okay. So still orders of magnitude off of the lock-in, but yeah, that's pretty good that you got 83. But the lock-in, you can get much higher, 10 to the 5th or so quality factors, and it's really just by like pushing buttons. It's not digging through all the electrical components and stuff. So the last thing I just wanted to touch upon, and this will help tomorrow with the Lab 5 worksheet, is just the layout of these lock-ins. And I just want to go over this because since you guys won't be using this in the lab, but you will be using these in junior or senior lab, or an upgrade of these in junior and senior lab. They're also Stanford Research Systems. So this at the top is the front panel. Back here is the back panel, and you actually need to use the back panel, not just for the GPIB connections, but also the reference signal for the lock-in amplifier. It has a built-in reference signal, and I think someone asked a question about this last week. So here is where you get your reference signal. So it has built-in sine or square waves. You can see what shape you want to use over here. But the weird thing is this is on the back, and you need to take a coax cable and connect it from the back to the front of the lock-in amplifier, which, why don't they just have this like internally built in? I don't know. Or why don't they put it on the front panel or even on the side? I don't know, but that's something to be aware of. Also, you can tune these. These are little trim pots up here that you can screw and adjust slightly. And you also probably want to put a T-BNC junction here to check on the oscilloscope what your actual reference signal is. So here is the reference input, and you can tune the phase, like I mentioned, the shape. Your signal inputs are over here, and tomorrow you'll be going over the difference between like the A, B, and I inputs. I mentioned that this can work from nanovolt to millivolt ranges, and it's very important to not overload. Sebastian, you had a question,
Yeah.
or the sound not working?
Yeah. How come there's no triangle wave reference? There's only like two different, a square wave, sine wave, and an offset square wave.
Mm-hmm.
Why is that?
Well, if we think about this in Fourier space, I would think that the sine wave has a single frequency, component. The square wave has those step changes. But if you're thinking about the different frequency components in the Fourier space, the square wave would be the most complex there. So I could see that as a possible reason. And also your reference input does not have to be the built-in reference. You can also provide from your function generator, you can provide other inputs as well. So I think for simplicity and that most people are looking for AC signals, that the sine wave or the square wave would meet most of their needs. And that's why those are built in.
Okay.
So with the sensitivity, I just want to highlight this again because it's very easy to overload if you have the instrument, if you have this at the wrong setting. So that's where this status comes into play. So this red unlock light is if your reference is plugged in and you have a reference, this red unlock light will be on, but right above it, there's something that's OVLD, that's overload. And that will tell you, okay, immediately remove your signal or change your sensitivity because you're gonna damage this like $3,000 instrument. So this is an instrument that's actually somewhat easier to break. So be aware of that and you don't wanna see overload there. There's also some built-in filters over here. So before you even multiply your signal and your reference, you can use these built-in band pass or low pass filters, and you guys will go over the diagram tomorrow to understand what those are. But that's, again, if you're looking at very low signals or at a very high sensitivity, these signal filters can help you avoid overloading the lock-in amplifier. And then we already talked about the time constant, but then the output is here in the center. So you can get a digital output, connect this to an external instrument like the DSO or your KDMM. But there's also, like I mentioned, this analog output here, which is sometimes nice to use to see, like, are you having an AC signal? Seeing this, I guess this arm go back and forth can show you if you're getting closer and closer to a DC signal or if you're still seeing oscillations take place. So I think that's why they have this analog display here to help emphasize if you're in a DC condition or an AC condition. And just to emphasize again with these inputs, with the range, you don't want to ever go over 10 volts for the AC or 10 microvolts for a current, because that's the limits for the lock-in. So just like in Lab 1, where you want to understand the limits of your instrumentation and their sensitivity, the user manual will have information here about that. Yeah, so that's most of what I had. Any questions with the lock-in?
You said we were going to use a version.
Sorry, the sound was cutting, Robbie.
I'm sorry, did you say we're using a simulation or a simulator of the lock-in amplifier?
Yeah, so next week you'll use, yeah, it's like a simulation.
Is it like a GUI, like an interface we're interacting
Yeah, it's
with?
like it's a GUI, so it's not gonna be this exact instrument. So tomorrow there's a YouTube video where they're gonna be using a very similar one. It just has 2 inputs instead of 1 input. So that video is gonna be emphasizing like using this instrument, but the GUI type simulation, it's through LabVIEW environment. That's going to be giving you an idea of like, okay, what would you actually see like on this output analog meter or the output on your DSO. So display there. Anything else?
What did you say the maximum current was again?
So the maximum current is 10 microamps.
Okay.
So pretty low.